Hello, my name is Matthew Stevenson, and today I'm presenting my Capstone Project, Measuring AI Model Collapse Caused by Synthetic Data Contamination. Over the next few minutes, I'll walk you through the problem, the research that inspired it, how I approached the experiments, and what the results mean for future AI development. Large language models, like the ones powering modern AI systems, risk what's called model collapse when they're repeatedly trained on AI-generated data. Over time, that can cause the outputs to lose diversity and realism, which impacts accuracy, fairness, and reliability. On the screen is an illustration showing what happens when real data feeds into a model, the model produces synthetic data, and that data gets fed right back into training. Over enough cycles, the system essentially eats its own tail, pun intended, and the variety in its responses starts to shrink. Earlier research shows this collapse happening in two distinct phases. First, rare and unique events in the data disappear, and later, outputs converge into repetitive, low-variance patterns. Another line of research modeled this process statistically and found that when models train repeatedly on their own outputs, their probability distributions inevitably narrow into a single dominant pattern. Other experiments confirm these effects across multiple languages and domains, so we're not just seeing an English-only issue, it's a broader risk for any model trained on synthetic content. So, the question I set out to answer was, how does progressively adding synthetic data to fine-tuning impact the quality and diversity of a model's outputs? My hypothesis was that as synthetic contamination increases, the model's performance would degrade in measurable and predictable ways, and that we could capture this degradation with both numerical metrics and qualitative review. For this project, I worked exclusively with the GPT-2 QA dataset, a single set of instruction response pairs. The model used was GPT-2 with 117 million parameters, fine-tuned and evaluated on Hugging Face. The experimental design had two main parts. First, I tested the impact of different levels of synthetic contamination in training data, 5 levels in total, from 0 to 100% synthetic content. Second, I ran a multi-generation test where a model trained on human data produced synthetic responses that were then used to train another model. This setup allowed me to examine both the direct effect of contamination and how degradation compounds across generations. Initially, I measured only evaluation loss and perplexity. I trained on the human dataset and progressively more contaminated datasets, but in some cases, loss and perplexity actually improved with higher contamination. That was a red flag for overfitting. The model was getting better at the test set, but worse in output quality. So, I expanded the metrics to include n-gram diversity and entropy, plus a qualitative review of multi-generation outputs. These additional measures told a different story. Across contamination levels, diversity steadily dropped, and the meaning in output broke down, even when loss and perplexity looked fine. These deeper metrics confirmed the collapse. Less variety, more redundancy, and a measurable loss in richness as synthetic content increased. Synthetic contamination erodes model quality, even at low levels. To wrap up, this study found that even modest levels of synthetic contamination can noticeably degrade model outputs. This isn't just my observation, it matches what prior research has been saying, especially the loss of diversity and coverage of rare events as contamination increases. From a practical standpoint, the message is clear. If we want to maintain reliable, high-quality AI models, we have to preserve and prioritize human-generated data in our training pipelines. Once that original data is diluted or lost, performance and trustworthiness suffer. Now, it's worth noting that my test used a relatively small GPT-2 model and only a limited number of contamination generations. So, future work should explore whether the same patterns hold, as well as how severe they become in larger, more complex models. I'd like to thank everyone whose existing work and ongoing efforts contributed to the success of this project.